Hello, everyone. So I introduced myself. I'm Matteo Pelati, and I'm heading the data engineering at DBS Bank in Singapore. Here with me is Chandra, that will introduce himself. So we're going to give you a talk. We're going to give a talk about how our journey through how we ended up building interactive application based on Spark to allow interactive usage of Spark to our internal bank users. Chandra?
Hello everyone, this is Chandra and I'm from Singapore DBS Bank. Okay, so let me give you a quick intro about what DBS is like. So DBS is the development bank of Singapore government, and it's the largest bank in Southeast Asia with the US $400 billion assets. It's the world's best digital bank in 2018 as published, and DBS is undergoing a complete digital transformation actually, and we are building a data platform and putting all the data of the bank at the center of in the data platform, and requires complete data and lots of services in order to ingest, compute, and then serve the data to different reports or dashboards, right? So it's a self-service model that we are trying to build, and whatever we will be talking today is about one of the app that we have built as a part of this journey, okay? So what would the typical development process in a bank looks like, right? So business analysts will be defining their processing rules, and development or the dev engineers implement those rules in Spark, and then dev test rules in the development and UAT environments. So this is an iterative process. So you have to write the job locally, deploy, send it for UAT testing, and test it with some sample data. You will get issues, debugging and fixing it. So this is a cycle. This is a cycle that happens in an iterative development and testing. So what if we have an interactive way of validating your results? So that's what we will address. So the business analyst tests the rules in production, and the job goes live. So this is the typical development process that we follow, but what changes we have done, or what are we bringing in? So we want to enable the BAs to write, test, and deploy Spark jobs. So they don't need to code anything, but they just need to configure some rules, or they need to know how SQL works. So BA needs an easy way to work with the real data interactively. So the thing is, the data resides somewhere in the cluster, and you have to access the data, and you write some sort of code on Spark Shell, but you cannot validate your results. So this is the thing that we experienced, because when the BAs, all these people come from the background of SQL assistant of Teradata or Oracle Studio, that kind of experience. So we have to facilitate them something to develop interactively and validate the business logic, what they have been implementing till date, right? So they need an easy way to port RDBMS applications into Spark. So that's what we bring in. So why did we develop this? So there are many tools out there which does interactive way of applications on top of Spark, like data wrangling tools, job monitoring tools. There are lots of machine learning tools. So our goal is simple. So you shouldn't be required to know coding in order to write Spark jobs. So that's the goal. So typically how we achieve is we have a rules, we can IntelliSense rules, and we enable BAs to write their business logic using some SQL grammar. So that's what we are going at. So this is inside of our tool. So typically, it looks like there are some set of inputs, and you can write SQL, and you can see the lineage and results. So we are also having another talk tomorrow, so we will be talking about this tool completely then. So this is an interactive glimpse of how we do Spark coding interactively. So our journey, so we started from basic Spark, Hadoop, and YARN, and how it evolved into an interactive set of application. So having a set of REST server, security, and then writing applications, all through interactive model. So Okay, what I will do is I'll conclude this part here, and I'll hand it over to Matteo, who will take you through the entire journey of how we are doing it.
Okay, so Chandra gave you an introduction of the tools that we have developed internally at DBS. The goal of this talk is not to talk about this tool actually, but is more about to talk about the journey that brought us to build this tool and how we built it. If you're interested in the tool and all the features specific for the tool, we're going to have a talk tomorrow about that. So let's talk more about typical Spark applications. So typical Spark applications are batch application. So the most basic application is something running on Hadoop YARN, where you have your batch Spark job, computing some results and writing results out to the file system or the data set. Now, we started with this like any other company, any of you, I think, but we wanted something more. So we wanted something that where the user can interact with the Spark context itself, with the Spark with the Spark job running in the backend. But of course, we need additional services. We need authentication. We need REST APIs, and as we showed before, there are several applications that are already using this concept. Actually, the Spark itself, actually, the web UI of the Spark itself, is nothing more than some REST API hosted in a YARN container. So, going back to the journey. So, as I was mentioning, first it was Hadoop and MapReduce. Then we have something a little bit more complex where YARN is introduced actually, and YARN basically handles the entire life cycle of an application and Spark running on top of it. Now, as you see more and more long-running applications, Spark long-running application, that you basically you're not bound just to run a batch job on top of YARN, but you can use the YARN container that is allocated when you run your Spark job to build something more complex than that. And that's where we ended up. So basically, you can see in the last section where we have our Spark long-running session exposing additional services, which is running on top of YARN or Kubernetes. We have a caching layer, and then we have the file system, which can be S3 or HDFS. So, as I was saying, this is not a simple batch job, but it's something that is more interactive. We need a web UI that allows the user to interact with the data that lives directly on the cluster. And this is exactly that the UI that Chandra was actually showing before, that this is the UI that is hosted in a YARN container on top of a Spark context that the user can actually interact with. So the application is not just for crunching data itself, but is for doing a bunch of other stuff. For example, is managing metadata. We have this concept of metadata, which is basically what all the dataset definitions that we have in the bank. So we need to interact with this metadata. We need to look up these datasets, and we need to be able to compose a job. So we are not simply loading some dataset, processing, and emitting the output, but we do several operations. The other requirement is that this must be multi-tenant. I will go through the journey of the multi-tenancy. For now, I'm saying we have to be able to handle different users, different binaries, and I'll explain you why later, a different version of the binary, and different configurations as well. So we have to basically allocate multiple Spark contexts with different configuration. And we need a role-based security model because being this an interactive application, obviously there is a user logging in and a user interacting with the data. So all the security need to be enforced by the application itself. So this is how we started, okay? So if you think about an application where you create a long-running Spark context, and then you have a bunch of other services that interact with this Spark context. So at this point, the Spark context start being more like a service that provides that is accessible to REST API rather than the bad job. And the other services that are bundled with the Spark context can provide different they can have different functionalities. They can bring up a web server as a REST endpoint. They can enforce security. They can access catalogs, etc., etc. Now, when you run a Spark context, you have obviously the driver allocating the context plus a bunch of executors that are doing the data crunching. But as you can see here, we have the Spark context and a couple of microservices, okay? But this implies that obviously the Spark context allocate on its own, the Spark context service, let's say, allocate on its own the executors, and we have some microservices that are basically providing other functionality, but they are residing within the same YARN container. So we didn't want to be limited to that. So we say, okay, so let's use YARN as for what is it? So it's a distributed application, let's call it operating system. And we want to be able to basically allocate multiple containers and multiple YARN containers. And one of these containers can actually host a Spark service. We have other microservices that are hosted in a container, but this can be spread everywhere across the cluster. So I can have like 5 containers with different services, and even replicated services actually for redundancy. So we start to create a model of like deploying an application that is all microservices based on top of a YARN cluster. So a microservice can implement any functionality. It can be a REST API server, it can be a metadata store interacting with the metadata manager, or it can be a Spark executor. So at this point, the Spark context becomes just another service that can be user can interact with. A microservice can run within the same YARN container, as I said before, or across multiple YARN containers. So I might want to have multiple services running in different containers, or even the same service running in 2 or 3 different containers for load balancing, for example. The other requirement, obviously, when you start designing this is that microservices, at this point, they need to be auto-discovered. So we have 5 or 6 YARN container. One of the microservice in the container is actually a Spark session. And at that point, when I want to interact with microservices, I need these services to discover each other automatically. For this reason, so this has been like a journey for some times, actually. And what we have built a library that allows us to basically build microservices-based application on top of YARN. So this library basically perform a very simple task. One is service discovery. So it uses Zookeeper to basically enable service discovery across your cluster. So each service is published and can be accessed by any other service. It uses Java interfaces as contracts. So basically your interface is published to Zookeeper, and you can look up the service by simply looking up the interface name. And if the service is available locally, it will look it up locally. You can use it locally. If not, service is not available locally, it will basically take care of doing an RPC to the remote service. As I was saying, it takes care of all the communication using RPC. And it supports deploying microservices with different semantics. What do I mean here? Like I said before, I might have different microservices with different paradigms, actually. So I want to have a failover scenario. So whenever a microservices doesn't work, I want to fail over to another services. I want to load balance my calls between my YARN containers and across the cluster. I want to have a single instance running. Think about like a scheduling service where you need to have only one instance running, and if that instance goes down, there must be a leader election mechanism that basically determine who is going to be the next leader. And of course, partition balancing. Basically, if we want to partition our calls through some partitioning key. So this is the picture that started being built. So we have our YARN application, we have our Zookeeper, and then we have multiple containers, each one of them hosting the beanszeg library that takes care of service discovery and RPC, a bunch of microservices, and one of these microservices being a Spark context, actually. So at this point, we start having a picture of a complete YARN distributed application where we have multiple services. We have a Spark context that we can interact with directly to perform some operation interactively. This is just an example of how the microservice model work actually with beanszeg actually. So you can simply say, okay, in my service directory, I want to put a service, and in our case, it's going to be a Spark executor service where we can invoke APIs, and then from another container, I can basically look up that service and start invoking call of that service actually. So this is what we call our kernel, okay? So our kernel, that is the name is taken from the noteboot kernel actually. So here we have a bunch of services, and one of the service is basically a REST API server. Now, from the UI, when you start interacting with the data, what happens is that REST API server basically invokes another service, which is the Spark executor, the Spark microservices, to launch interactively the processing of the data. So this allows us to have a very interactive way of accessing the data, crunching the data, and letting the user test on the real data on the cluster itself. Now, this is the point I wanted to bring up about user concurrency. So we deployed this. We had several users started using it. so the problem that we started seeing is that, we were hosting one single Spark session, and multiple users were accessing the same session with different operations in a multi-threaded way, actually. So this created some problems, and of course, first, performance problems, obviously resource contention problem, and the other requirement that we had was about security model. So not every user needs to have access to the same data. So we said, how we're gonna solve this issue? So we said, okay, we can have one interactive application, and consequently, it's going to be one Spark session per user. So the Spark session now is not shared, but every resource, all the resources are allocated per user. So we can pre-allocate the resources. We can bound, we can upper bound the resources for each user. Each application can be started with different configuration, because that's what we require. Each user which belongs to a different group will require different metadata catalogs, for example. The user can spin up multiple instances with different runtime version. For us, this is very important. Whenever some jobs are built, the user has to be able to rerun their own jobs with the specific version, with the specific binary version that they built the job originally with. And by having multiple applications being spun up, we basically allow the user to decide which version of the binary he's going to use. And as I was mentioning before, data access permission. So in a Kerberos cluster, when you spin up an application, you spin it up with your GitHub. And that GitHub determines all the rights that you have on the data that you're accessing. Now, obviously, having multiple users sharing the same application and the same context, this is not possible. So we said we need a way to allow each user to use its own GitHub and enforce the proper security permission for each user. So now the application started being more complex, and we introduced two different components. One is the application kernel that you saw before. It's basically the interactive Spark application. And the other one is actually the application launcher. The application launcher is just a component that takes care of doing all the stuff that I was mentioning before. So one is performing user authentication. The second one is the configuration and the binary version retrieval. So the user can say, I want to start my binary version 015 with this configuration. And at that point, based on the user, the launcher takes care of retrieving the specific GitHub for that user, for that group. Once all this information is gathered, all these artifacts are gathered in a staging area, the kernel is spun up, and with the proper GitHub, with the proper binary version, with the proper configuration, etc., etc. Now, this is a overview of the launcher, and you can see that we have even here. This is an application running on an edge node, and we have a user authentication. At this point, the user authentication it performs the LDAP authentication. It loads the specific configuration for the kernel for that user. It loads the specific GitHub for that user, and the kernel is launched using basically a Spark submit on the cluster. Now, when the application is spun up, obviously, we need to basically redirect the user to the application page. For this, we use the functionality of beanszeg that allows us to perform service discovery. So basically, we can find out where the application is running on which node the application is running in the cluster, redirect the user there, so the user can start interacting with the Spark session directly. This is a complete overview of how we got from the original batch job through our journey. And this is what basically we ended up. Our kernel exposing the REST API with the web UI, plus the launcher, which take care of what I just described. So this is pretty much it, actually. Thank you all for everybody, and this concludes our talk. Any question?
Raise your hand if you have a question, and I'll run the mic over to you.
Hi. Do you enable to predict a machine learning model online? If the solution that the architecture that you show us enable to predict on machine learning model online to the channel, to the end channel.
So basically, I mean, this is just this is a, let's say, a generic way of building an interactive application. So our purpose for this was not machine learning, but it's basically enabling BA to work interactively on the data. But you can easily apply the same design to any application that also does machine learning that requires interactivity, actually. So you can take the exact same design, apply to, I mean, as there are many other applications doing this, like for data crunching, machine learning. So this model can be applied to pretty much anything that requires an application to be interactive.
Yes, hello. Thank you for a very interesting talk. I have a few questions regarding the very front end of your application. So there are some projects, for instance, called Livy and another project called Zeppelin. Have you developed your own flavor of these, or have you utilized some of these, for instance, as the REST API?
Not really. The REST API here is just, so everything is hosted into the YARN container. So the REST API here are basically a Jetty server that is enclosed in a microservice, actually. So that's a very, very simple. We didn't, I mean, of course we use libraries. We didn't use any library that is specific to this, because at the end of the day, a microservice for us is just a class exposing some functionalities, actually. So it's there is nothing specific that we use for this this model. But basically, talking about the REST API is nothing more than a Jetty server that is embedded into the application itself.
All right, we have time for one more question.
Thank you first for the presentation. And I would like to ask, because right now each user has his own Spark job, and what about the latency of this application?
You're talking about the latency of starting an application or using an application?
Starting, actually.
Okay, starting an application, yes. I mean, application can, depending on how the cluster is busy, it can take up to 1 minute, I would say, actually. But, you know, this is not really a pain for us because, you know, usually our user, they start up an application and they will use the application for hours, actually. And we have a timeout mechanism. So the application is spun up. If the application is not used for 30 minutes, the application automatically dies. Of course, there is this lag of up to 1 minute when they start the application, but so far we haven't got any complaint about that.
Awesome. Well, thanks
Thank
for
you.
the great presentation. Let's give him
Thank you.
another round of applause.